Here in section 7.4, we're going to look at integration of rational functions by partial fractions. So to motivate the topic here and to get the basic idea, let's consider a simple algebraic problem of combining two rational expressions by, of course, getting a common denominator. So for instance here, of course, we can multiply the first fraction 2 over x minus 1 by x plus 2 so that it has the same denominator as the x plus 2 over here, and then similarly multiply 1 over x plus 2 by x minus 1 over x minus 1 to get a common denominator there. So here our common denominator would be x minus 1, x plus 2. And then simplifying the expression in the numerator, we would have, let's see, 2x plus 4 minus x plus 1, which then we can combine some like terms and we get x plus 5 in the numerator. And of course you can also FOIL out the denominator. You see you'd have x squared plus x minus 2. Okay, so in this case what we did was we found the common denominator to combine these two simple rational expressions into a single rational expression. And now suppose I wanted to integrate this function x plus 5 over x squared plus x minus 2. As it is, perhaps it's not obvious what its antiderivative is. But if we notice that what we did here showed that this expression is in fact equivalent to the one that we started with, so the integral of x plus 5 over x squared plus x minus 2 is equal to the integral of 2 over x minus 1 minus 1 over x plus 2. This is in fact much easier to integrate because then each of these is a simpler function to integrate. 2 over x minus 1 when we integrate will be 2 times ln of x minus 1 minus the integral of 1 over x plus 2, which will be ln of x plus 2. And so once it's in that form, it's much easier to integrate. Okay, so the basic idea is that here we're going to be looking at the rules that will allow us to do this process that we did here in reverse. In other words, we want to start with an expression like this. We want to go backwards and split it up into an expression like this. Okay, so in a sense what we're doing is we're expanding out this rational expression into a sum or a difference of simpler rational expressions. And to start, one thing we need to consider is whether what we have is a proper or an improper rational expression. So when we say proper, it means that the rational function, say I have f of x equals p of x over q of x, where p and q are polynomials. We will say is proper if the degree of p in other words, the degree of the polynomial in the numerator is strictly less than the degree of q. So if the degree of the polynomial in the numerator is less than the degree of the polynomial in the denominator, then we say it's a proper rational function. Okay. On the other hand, if it's improper, Well, what do we do? So improper meaning that p of x over q of x is improper if the degree of the numerator is greater than or equal to the degree of the denominator. In this case, it can be reduced using long division, using polynomial long division. Into a form where we have f of x plus, say, r of x over q of x. Okay, where r of x is our remainder from doing the long division, where r of x over q of x is proper. Okay, so this is our goal here, is that if we see that we have an improper rational function, the first thing that we need to do is perform long division to reduce it into a form where it's got that proper rational term. So let's try this out with just a simple example here. We've got the integral of x cubed plus x over x minus 1. We notice this is improper since the degree of the numerator is degree 3 and the degree of the denominator is degree 1. So since it's improper, we need to use long division to reduce. Okay, so hopefully you remember how to perform polynomial long division. In this case, we'll start with x cubed plus x divided by x minus 1. Now I give myself a little gap here because it's missing the x squared term, so we can kind of line up the like terms when we perform the division. And the way we start is we start by dividing just the first term here, x cubed divided by the first term here, x. So x cubed divided by x will be x squared. And then I multiply x squared times x minus 1, and I put that below. So we'll have below x cubed minus x squared. And then we subtract that from above. And so that gives me x cubed minus x cubed. Those terms cancel. And then there's no x squared term here, so we imagine we'll just have 0 minus negative x squared, so plus x squared. And then I'll drop down the next term. So plus x. And then we repeat. Now I'm going to take x squared here, the first term, x squared divided by x here, plus x. So that'll be the next term. So I'll multiply x times x minus 1. So I'll have x squared minus x. And then I subtract it from above. And that gives me, see, x squared minus x squared, those two terms cancel, and then x minus negative x will give me 2x. Okay. Notice there are no terms to drop, so nothing left to drop, but I can still divide. In other words, 2x can still be divided by x here, since they're both degree 1. So we'll do one more division. 2x divided by x is 2, so I'll put plus 2 here for the last term. And then 2 multiplied by x minus 1 will just give me 2x minus 2. And again, I'll subtract it from above. And let's see, so then I'm left with 2x minus 2x is 0. And then minus negative 2 will be plus 2. And now I see that 2 is a lower degree than x minus 1, so that leaves me with my remainder of 2. And so what we've done here is we've rewritten x cubed plus x over x minus 1 as, here's our quotient, x squared plus x plus 2. and then plus the remainder, which was 2 over the divisor, which was x minus 1. Now we've expressed it in a form now that's much easier to integrate. So now I can just integrate each term. So x squared, of course, 1/3 x cubed plus 1/2 x squared plus 2x, and then the integral of 2 over x minus 1 will be 2 times the natural log of x minus 1. Okay. So you see that once it was in this form, once it was in this form where we divided, then we were able to integrate it one term at a time, because here the remainder term that we got is now a proper rational function, and it's in a form where we can integrate.